Welcome back to part 5 of zeros of polynomials. We are now going to kind of put everything together, and we're going to finish up by going back to the beginning where we had a rather large polynomial p of x equals 32x to the fourth minus 76x to the third minus 191x squared minus 71x plus 12. And we were kind of, I don't know about you, but it is a little overwhelming the first time you see Descartes' rule of signs. And here they all are. I have them listed again here for you. And I've crossed out all the doppelgangers. So any fractions that are equivalent, I've left only one of them, and all the rest have been crossed out. So we're left with this lovely pile of possible zeros. And so what we need to do is graph it. And then we'll also use the upper and lower bounds theorem to make sure that we have seen enough of the graph to be confident that what we are restricting our zeros to aligns with what we're seeing on the calculator. So we have 32x to the fourth minus 76x to the third minus 191x to the second minus 71x plus 12. And then I'm going to make sure my window is reasonable. So I'll go down to Z standard just to start out and graph it. To me, it looks like we have a zero around -1, somewhere right around 0, and then something close to 4. And it also looks like it goes quite high and low here, and it's outside of our window. So I'm going to make my max and min y values just a little bit bigger. And I'm going to restrict my x values from like -3 to 5. And then I need to show that what I'm seeing are all the roots. Let's see what this looks like. Okay, this is so much easier to see. It doesn't show all the minimums, but it shows enough and close enough that I can make some educated guesses. I have 1, 2, 3, 4 roots. The degree of my polynomial is 4, so there's a good chance that those are all my roots, which is convenient. But let's just show that we've got this upper bound and lower bound going on. If I were to pick -2 to show that -2 is a lower bound of this polynomial, so let's go ahead and do that first. So I want to show that my lower bound is, let's say, -2. So if I use -2 with synthetic division, let's go ahead and drop down 32. -2 times 32 is -64. -64 plus -76 is -140. A -2 times a -140 is a positive 280. -191 plus 280 is 89. -2 times 89 is -178. -71 plus -178 is -249. -2 times -249 is positive 498. Plus 12 is positive 510. Now, if you look at these, they are indeed in alternating signs. And so this is a lower bound. Okay, so let's check to see if our upper bound is possibly, again, looking at our graph, 1, 2, 3, 4. Let's see if our upper bound is 4. Let's just use 4. That'll be more convenient, I think. In synthetic division, drop down 32. 32 times 4 is 128. Negative 76 plus 128 is 52. Times 4 is 208. 208 minus 191 is 17. 17 times 4 is 68. 68 minus 71 is negative 3. Negative 3 times 4 is negative 12. And we have a 0 as a remainder, which means that 4 may not be an upper bound because of this negative 3, but we found a 0 of the polynomial. We didn't show that 4 is an upper bound, but it is a 0. So now we can rewrite our polynomial p of x as one factor x minus 4, and the remainder is 32 x to the third plus 52 x to the second plus 17x minus 3. And now we need to figure out what the remaining factors of this are. If you're feeling overwhelmed, that's perfectly normal. So before we go into any more great detail about upper and lower bounds, we know that negative 2 was a lower bound. I can erase all the possible negatives that are more negative than negative 2. So negative 6 is not an option, negative 4 is not an option, negative 3 is not an option. If I take a glance at my graph, I can see that 4 was clearly a possibility. It also looks like negative 1 might be one of the roots. So let's see if we can show that negative 1 is also a 0 of the polynomial. So now that I know that x minus 4 has factored out, I'm going to use my degree 3 polynomial now. I am not going to go back up to what I started with. Don't use your original p of x once you have factored one of your factors out. So 32, 52, 17, and negative 3 are my new coefficients. Dropping the 32 down, negative 1 times 32 is negative 32. 52 minus 32 is 20. Negative 1 times 20 is negative 20. 17 plus negative 20 is negative 3. And a negative 1 times a negative 3 is a positive 3. Negative 3 plus 3 is 0, and we found another 0 of our polynomial. Notice that at this point we could write our polynomial p of x is equal to x minus 4 times x plus 1 times the remainder right here, 32x squared plus 20x minus 3. Now, before you try and do anything fancy with synthetic division, what you should be thinking about is taking this quadratic that I just found, the remainder of my second set of synthetic division, and putting that into the quadratic formula. X is equal to negative b plus or minus the square root of b squared minus 4 times 32 times -3, all over 2 times 32. So the square root of 20 squared minus 4 times 32 times -3 will just be plus or minus 28 because that is a perfect square. So I will have x is equal to -20 plus or minus 28 all over 64. This will give me two solutions. I will have -20 plus 28 over 64, and I will have -20 minus 28 all over 64. This gives me 8 over 64 and also -48 over 64. 8 over 64 is just 1/8. That's one of my options. And the other one, let's see if this reduces. We could have a -24 over 32. And the last one we have is a -3 over 4. So our final polynomial factors could be written in the following way. P of x is equal to x minus 4 times x plus 1 times, notice the 1/8 would be equivalent to 8x minus 1, and the last would be 4x plus 3. These are the factors of the polynomial p of x. And yes, it almost took a whole page of paper, but you can show all your steps. You can prove that you haven't missed any of the roots outside your window, and you sometimes even luck out and can show that one of your bound checks actually comes out as a root. This is the lovely thing about using your calculator for this process.